Welcome pre-cal students to class today on Wednesday the 22nd. Hope you guys are doing well. Hope you're ready to learn some math today. Caleb and Matthew, you will have a test on Monday. If you're not going to come to my house on Monday, please let me know no later than Sunday. All right? Quizzes are due by today, so please make sure you have them turned in. 5 points off per day that the quizzes are late. Your integrity sheets. When you walk in the door on Monday, anything you don't have done, you can still do it, but you won't get credit for it. So when you walk in the door Monday, would you please have your integrity sheets filled out? I know that I did not give you new sheets, but you can write down on a sheet of paper all of the assignments that you've done, or at least the days and the dates. We're going to talk on Monday about your review sheets. I'm going to let you guys choose whether you want me to continue making review sheet videos for you, which I do not mind. I'm getting paid to do a job, but if you're not going to watch them, if you're going to come in Monday and ask questions, then there's really no need for me to do that. So we'll talk about that on Monday, and if you guys cannot agree, then I'll just go ahead and make the videos, and that's fine. It doesn't matter to me. The video is long again today, but there won't be any homework, okay? So please understand that. And then tomorrow will be homework only with no instructional video. Now, let me say something. Did you notice yesterday there were 2 videos? Always look at the dates, guys. The one video was, I don't know, 2 minutes long, 3 minutes long. It was just going over announcements like this right here. So when I say that tomorrow there will be no instructional video, there still might be 2 videos. Always look. And if there are 2 videos, the one video will be 1 to 2 to 3 minutes long. It'll just be going over announcements like this, okay? So please understand that, and please look for that, okay? Please call me or email me if you have any questions at all. I hope you guys are doing really well. I'm here to help you as your teacher if you need any help, okay? Let me get a drink of water here. Put your seatbelts on, buckle up. It's going to be a long ride. But remember, at the end of the ride today, there'll be no homework, okay? Here we go. We have been studying sequences and series. Remember, a sequence is a list of numbers like this. Let's see, 1, 2, 3, 4. And a series is when a list of numbers are being added. So instead of having commas, you would have plus signs like this, okay? That's a series. I'm just reviewing a little bit, okay? We are going to be studying 2 types of sequences series. We have already studied one. Remember, we looked at it 2 days ago on Friday, and we did homework on it yesterday. They're called arithmetic sequences and series. Today, we are going to look at the second type, and they are called geometric sequences and series. So one type is called arithmetic, the other type is called geometric. And these are the 2 types of sequences and series that we're going to be looking at. Copy down your heading, please. Today we're looking at geometric sequences and series, lesson 10.3, and I encourage you to always write the date down. Actually, it's 2014, isn't it? There we go. Okay, so please copy that down, and remember my philosophy. I go fast on purpose. You can always pause the video, but you cannot speed it up. So I'm going to go fast, and there'll be plenty of times today that you'll have to pause the video. Here's the definition of a geometric sequence. A geometric sequence is a list of numbers in which each term is being multiplied by the same number. Now remember, an arithmetic sequence was when each term has the same number being added over and over. A geometric sequence is when each term has the same number being multiplied over and over. Let me give you an example. Here are some examples. 3, 6, 12, 24, 48. 3 times 2, 6 times 2, 12 times 2, 24 times 2. Do you see how I did that? Every number here is being multiplied by 2. By the way, remember in an arithmetic sequence, we had the expression common difference. Do you remember that? And we denoted that by the letter D. Please make note of this. In this example here, we have a common ratio. That's what it's called, a common ratio. And of course, the common ratio is denoted by the letter R. And in this sequence right here, the common ratio is what? 2. Because what number is being multiplied over and over and over? 2. So arithmetic sequences have common differences denoted or symbolized by the letter D. Geometric sequences have common ratios and they're symbolized by the letter R. Okay, so the common ratio for this is 2. Now, by the way, some are not really easy to see. Remember in an arithmetic sequence, if I had 1 plus 2 plus 2 plus 2 dot 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 dot, and I told you to find the common difference, and if you couldn't see it, I told you to take any number you wanted and to subtract from it the term right before it, so 5 minus 3 is 2. You should remember that. Of course, most of them you can just see automatically, but look at this next example here. Finding the common ratio might not be very easy. So here's what you do. You pick any number you want in the sequence. I'm going to pick this one. And then you divide it by the previous term. So you would take negative 1/8. Let's try it up here real quick. See this 12? Take 12 and divide it by 6. And when you take 12 divided by 6, what do you get? 2. And the common ratio is 2. So down here I'm going to take negative 1/8 and I'm going to divide it by positive 1/4. Now, of course, when you're dividing fractions, you flip the second fraction and you multiply. And a negative times a positive is negative. 1 times 4 is 4. 8 times 1 is 8. Reduce that and your common ratio is negative 1/2. Now, Mr. Earhart, does that work with these numbers? Sure. You could take 1/4 and divide it by negative 1/2 and you would get negative 1/2. You could take negative 1/2 and divide it by 1 and you will get negative 1/2. It doesn't matter which number you choose, students, as long as you divide it, not subtract. Now, you subtract when you're dealing with an arithmetic sequence. When you're dealing with a geometric sequence, you take a term and divide it by the previous term. You can do any term that you want as long as you divide it by the previous term. So now in this last example, and hold on one second, let me get out my notes because I have all of these worked out already. Hold on one second, please. But why don't you go ahead while I'm digging for my notes, go ahead and find the common ratio for this sequence, okay? And trust me, it is a geometric sequence. Trust me, it is, okay? So go ahead and find the common ratio. Remember, pick any number you want and use your calculator and divide it by the previous number. Or you could take this number here and divide it by this number. Or you could take this number here and divide it by this number. By the way, what if you wanted to check and make sure that this was a geometric sequence? Well, take any number you want, divide it by the previous number, and by the way, here's what you should get. You should get 0.75. So if this is truly a geometric sequence, you should be able to take 5200 times what? 0.75 and get this out. Then take 3900 times what? 0.75 and get this out. And then take this number times 0.75 and get this out. And by the way, if you test it, you'll see all of these numbers are being multiplied by 0.75. So it is a geometric sequence and the common ratio is 0.75. Let me get a drink here. And I hope that makes sense, students, okay? If not, back it up and watch it again. You really need to know this, okay? Just like there is a formula for finding the nth term of an arithmetic sequence, here it is. Remember, we looked at this for the past 2 days. We've been using this, okay? There is also a formula for finding the nth term of a geometric sequence. And here's the formula, and you need to know this, okay? You need to be able to tell the difference between when you have a geometric sequence and when you have an arithmetic sequence. For example, if I said 1, 5, 9, 13 compared to 1, 3, 9, 27, you should see right away this is an arithmetic sequence because you're adding the same number over and over and over, 4, 4, 4, so the common difference is 4. Right away you should see this is a geometric sequence because you're multiplying 3, 1 times 3, 3 times 3, 9 times 3, so your common ratio is 3, okay? You should be able to tell the difference, and thus you should know which formula to use. This is the formula for the nth term of an arithmetic sequence. This is the formula for the nth term of a geometric sequence. This one here is brand new. This is the old one up here. So let's go ahead and get started. Find the seventh term. Well, first of all, let's see if we have a geometric sequence. We do. We're multiplying by 5 and we're multiplying by 5. So we know for sure the common ratio is 5. Now I guess very quickly with your calculator you could just multiply by 5 until you got to the seventh term. But the reason I don't want to teach it that way is on the test or a quiz I might ask you to find the 83rd term. And of course you're going to need to use the formula for that. So before we can find the seventh term, we first of all have to find the nth term. Why? Because once we find the nth term, we can then plug in the number 7 into this term and get out the seventh term. So let's quickly find the nth term. A subscript n equals a subscript 1, that's your first term, so 4. And then r, that's your common ratio, 5. And then n minus 1. Wasn't that easy? There's your nth term. And now let's find the seventh term. So where the n is, I'm going to put a 7. So I really have 4 times 5 to the 6th power. 7 minus 1 is 6. Now a lot of students, they like to take 4 times 5 first. And of course that's totally wrong. You do your powers first. Okay? So the first thing you would want to do here is take 5 to the 6th power, which I'm doing with my calculator now. 5 to the 6th power times 4. And if you do that correctly, you're going to get 62,500. So there, you found the seventh term. Now let's come down here and let's find the 10th term. Before we do that, let's see if we have an arithmetic sequence, or let's see if we have a geometric sequence, or what we have here. Well, it looks like we're multiplying by the same number over and over and over, and the same number is going to be negative 1/2. 64 times negative 1/2, 32 times negative 1/2, 16 times negative 1/2, so on and so forth. So my common ratio is negative 1/2. Mr. Arrett, how'd you know that? Well, it's like I taught you guys before. Just pick any number you want and divide it by the number before. 16 divided by negative 32 is negative 1/2. And then I tested it, and I took 64 times negative 1/2, 32 times negative 1/2, 16 times negative 1/2, and I saw that each number was being multiplied by negative 1/2. Now before I can find the 10th term, I must first find the nth term. So a subscript n equals my first term, which is 64. That's what the formula says. Don't miss the formula, guys. It's right here, okay? And then r, which is negative 1/2. To the n minus 1. Now I'm going to find the 10th term, so I'm going to put a 10 right here for n. So I would now have 10 minus 1. So I would have 64 negative 1/2 to the 9th power. Now if you're going to take negative 1/2 to the 9th power, you're welcome to type in negative 1 divided by 2 or negative 0.5. But you better listen to me. Whatever you type in your calculator, you better put parentheses around it. If you put negative 0.5, put parentheses, and then take it to the 9th power. If you have a graphing calculator and you type in negative 1/2, you better put parentheses around it, okay? So here we go. Negative 1/2, let me clear off my screen here. Negative 1/2 to the 9th power is going to be negative 0.0019533125, and then of course you multiply it by 64. And you can get out one of two answers. You can get out negative 1/8 or you can get out negative 0.125. But you do need to know how to get both of those answers out. In case I ask you for a fraction, then you want that answer, and if I ask for a decimal, you'll give me that answer. If you don't know how to do that, remember on a graphing calculator it's math, enter, enter. So you would take negative 1/2 to the 9th power, make sure you put parentheses around it, and then put 9 on the outside, equals times 64, enter, and then math, enter, enter, and you'll get negative 1/8. But the main thing I want you to learn is this: do you see how to find the nth term of a geometric sequence? It's pretty simple, and that's the form that you want. Let me get a drink of water here. Now, just like there is a formula for finding the sum of an arithmetic series, and there it is. This is old. This is from Friday and Monday. There is Friday and Tuesday. There is a formula for finding the sum of a geometric series. This is old, this is new, and there it is. Please write that down. Let's go ahead. Remember, I go fast, guys, so pause the video when you need to. Let's find the sum of the first 7 terms. Now, of course, this lesson is all about geometric sequences, and we can see right away we're multiplying by 5 over and over and over. All right. Now, first of all, let's go ahead and see if we can't find the sum of the first 7 terms. It looks like to me in this formula, all that we have to know is the first term, and we know that already. We have to know R, and we know that already. And then N is just how many terms you're trying to add up. And it says here we're adding up, we're adding up 7 terms. And so I think we're ready to use this formula. So let's find the sum of the first 7 terms. And by the way, what's really cool about this formula, do you even see the first 7 terms? No. Do you need to find the first 7 terms? No. This formula does all the work for you. So we're going to find the sum. We're going to find the sum of the first 7 terms. So I put a 7 right here, equals my first term, which is 3, times 1 minus, now R is 5, to the 7th power, and then close your parentheses. And then 1 minus 5. Now watch carefully how we do this, okay? First of all, we would have 3 times 1 minus 5 to the 7th power would be 78,125. Now you don't have to show all this work. I'm just trying to break it down for you and help you. In the denominator, I would have a negative 4, 1 minus 5. Now let's stop for a second. A lot of you are like, hold it, Mr. Earhart. When you typed in 5 to the 7th power, did you include the negative sign? No, I did not. And please don't do that. If you include the negative sign, you're going to miss the problem. Look, you're not taking negative 5 to the 7th power. Is the common ratio, you're taking R to the n power. Is R negative 5? Question mark? No, not at all. R is not negative 5. R is 5. So you're taking 5 to the 7th power, and this negative sign right here just simply gets brought down. Okay, you're not taking negative 5 to the 7th power, and that's different than what we did back here. In this problem here, it was actually R, the whole thing, 5, or negative 1/2, the whole thing, to a certain power. Okay, let's continue on. Now, obviously, I would next have 3 times negative 78,124 all over negative 4. And then next, I would have, unless I've made a mistake, in my numerator here, I would have negative 23,000 or negative 234,372. And again, for the second time, no, you do not need to show all of these steps. Okay, you do not need to do that. And the denominator is still negative 4. And then if you divide that correctly, you're going to get 58,593. So 58,593. I showed how that works so you can see exactly how to type it into your calculator. You do not have to show all of that work. You first take this number to the correct power, then subtract those two numbers, then multiply your top and divide your bottom. So this is a pretty cool formula. So you just added up the first 7 terms of this geometric sequence by using this formula right here without even knowing the 7 terms. Now let me say something. Remember, this formula only works with a geometric series or a geometric sequence. Okay, please don't forget that. Okay, let's take a look at this next problem here. Now I could give you one of these on a test, and the first thing you had better do is you had better make sure you have a geometric or arithmetic series. If you don't, then you can't use the formulas, okay? So let's check and see what we have here. First of all, I'm going to put a 1 in, and 0.3 to the 1 power would be 0.3, and then 0.3 to the second power would be 0.9, and then 0.3 to the third power would be 0.27. All right, now be very careful here. You do have a geometric sequence, and you are multiplying by the same number over and over. And if you don't see that, then please take a look here. And by the way, I did something wrong, and I apologize to you. I knew something, there was a pause there in the video because something wasn't adding up, and I apologize to you. I'm sorry. 0.3 to the second power is 0.09, and I'm sorry about that. And then 0.3 to the third power is 0.027. I knew something wasn't right. There we go. And then if you put a 4 in, 0.3 to the fourth power is 0.0081. Well, what you're going to see is this. We do have a geometric sequence. Okay? If you take this number here and divide it by this number here, you're going to get 0.3. And then what I'm going to do is I'm going to test that. I'm going to take each one of these numbers and multiply them by 0.3, and you do get out the next number. 0.3 times 0.3 is 0.09, 0.09 times 0.3 is 0.027, and 0.027 times 0.3 is 0.0081. So I do have a geometric series. I am adding up numbers that have a common ratio. All right, and so my common ratio is 0.3, as I just showed you. So I know that my first term, when I put a 1 in, is 0.3. I know that my common ratio is also 0.3. That's a coincidence. And then I need to know how many terms I'm adding up, the sum of how many terms. So now be careful. Remember how to do this. You always take this number minus this number. 11 minus 1 is 10, and then you always add 1 to that number. So we're adding up 11 terms. Or you could just say it's terms 1 through 11, so I know it's 11 terms. Either way, we're adding up 11 terms. So I know that my n is going to be 11. And now let's go ahead and use our formula. The sum of 11 terms equals 0.3, that's my first term, times 1 minus my common ratio, which is 0.3, to the n power, which is 11. All of that to the 1 minus r, 1 minus 0.3. Now again, you don't have to show all this work, but I'm going to really break it down for you, okay? First of all, 0.3 to the 11th power is going to be, well, it's going to be a really, I'll tell you what, if you type in go ahead and do this. If you type in 0.3 to the 11th power, you're going to get out probably something in scientific notation. It's probably going to say something on your calculator like 1.77147 e to the negative 6, which just means scientific notation. So here's what I would do if I were you. I would type this whole step in at once. So type into your calculator 0.3 to the 11th power, whatever you get, okay? And then somehow you want to take 1 minus that number. In fact, actually a good way to type into your calculator, and I apologize for being a little unprepared here, but I would type this whole thing into your calculator all at once, okay? So here's what I would type in. I would type in 1 minus, and then put a parenthesis right into your calculator, and then 0.3, and then close your calculator and put 11. That's what I would do, okay? If you do that correctly, you should get out something, and you're welcome to round it. You should get out 0.9999982285. I'm just going to put 0.9999, okay? And then in the denominator, you're going to have 1 minus 0.3, which is going to give you 0.7. All right, and now on your denominator, we're going to take that 0.999 and we're going to multiply it by 3, and we're going to get 2.9997 divided by 0.7. And if you do that correctly, you're going to get out approximately 4.28, 0.2 or 0.4. Hold on one second here. 4.2852, and it goes on and on. Okay, so there we go. It's just using this formula over and over and over. Okay, so this formula here is the formula for finding the sum of numbers that are a geometric series. Okay, all right, let's continue on. If you got to rewind it and watch it again. Okay, let me get a drink of water here. Okay, now we are going to get into something very cool and way out there. Are you ready? Watch this. This is so cool. What if I asked you to find the sum of this geometric series? Go ahead and write this in your notes. Now, you guys, if you've ever listened to me, it needs to be now. Please listen. Write this in your notes and listen. What if I asked you to find the sum of this geometric series? However, and it is a geometric series, you're multiplying by 1/2 over and over and over. However, I did not tell you how many terms. In other words, I didn't tell you if I want you to find the sum of 5 terms or 6 or 7. And you might say, well, Mr. Earhart, if you don't tell us how many terms we're adding, we don't know where to stop. It can't be done. You're wrong. This is so cool. You can find the sum of an infinite geometric series. You can? You can, as long as there's one thing that's true, and I'll get to that in a second. But let me show you first of all how you can do this, okay? You don't need to take notes on this, but you can if you want to. I'll leave that up to you, okay? All right, watch this. Here's a box. Now, my first number is half, so I'm going to draw a line cutting this in half. There. So my first number is represented by this shaded part here. Then next, I'm going to add a fourth. So I'm going to cut this in half, and now I'm adding a fourth. Next, I'm adding an eighth. Well, an eighth would be cutting this in half, so I'm going to cut this in half, and now I'm going to add that. Next, I'm going to add a 16th. Okay, well, if I add a 16th, I'm cutting this in half. Next, I'm adding 1/32. Okay, well, if I'm adding 1/32, that means I'm cutting this in half. Do you not see what I'm doing? I'm cutting the remaining space in half and adding it. Then I'm cutting it in half and adding it. Guys, I don't care if that space becomes this small. I don't care if it's minute. Can you not always cut it in half again? Sure you can. So this is so cool. You ready? I don't care how many terms you add. I don't care if you go out 100 terms. I don't care if you go out 100 terms. This box will never be filled up. And so what that means is the sum is getting closer and closer to what number? 1, because this box represents the whole number 1. But you'll never quite hit 1. So we say the number 1 is the answer to the sum of an infinite geometric series, or we say it is the limit. You can use either word. In fact, this book uses both words, so get used to it, okay? So if I asked you to find the sum of this infinite geometric series, or if I asked you to find the limit of this infinite geometric series, the answer would be 1. Now, Mr. Earhart, we have no idea how to do that. I understand that. I'm going to teach you how to do it. But I wanted to show you, first of all, that it is possible to not know how many terms you have and still find the sum, because it happens in some geometric series. Now, when does it happen? Well, that's a good question. I'm glad you asked that question, and here's the answer. Let me get rid of this real quick. And that is not what I wanted to do. Okay, now here's the key. Are you ready for this? Please take some really good notes and watch carefully. Here's the key. As long as your common ratio is less than +1 and greater than -1, then you can find the sum or the limit of an infinite geometric series. In other words, think of a number line. Watch this. Here's 0, here's 1, here's -1. As long as your common ratio falls in this area right here, it can't be 1 and it can't be -1. But all of these fractions in between, if your common ratio is any of this shaded in area, then you can find the sum of an infinite geometric series. And by the way, what was my common ratio? Do you remember? My common ratio was what? 1/2, and 1/2 falls right here in this area. So as long as your common ratio falls in this area, you can find the sum or the limit of an infinite geometric series. So this is a key note. I would write this down. Maybe you already did. Not all infinite geometric series. Let's stop right there. What's an infinite geometric series? It's just a geometric series. Numbers are being added and they have dots. Dot, 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 dot. So we know it's going on and on. It's infinite. Not all infinite geometric series have a sum. The only time an infinite geometric series has a sum is when, and here's what I just told you, is when r is less than 1 or greater than -1. That's the only time. Now I'm moving on. You know how I go fast. Pause the video if you need to, but that's the only time. So with that in mind, let's find, are you ready? Are you ready, guys? Let's find, and that's not what I wanted. Yeah, it is. Okay. Let's see. Let's take a look at this right here. Actually, I'd like to skip this and go on. So let's do this. Let's look now at the formula for finding the sum of an infinite geometric series. Now, guys, I understand this is confusing, but would you please trust me and listen to me? Let's go back. Remember when I gave you this formula right here? Right here, and I said that's the sum for finding, that's the formula for finding the sum of a geometric series, remember? Well, this formula here is used when you know how many terms. Remember, if in the two problems we did, one problem you knew we were finding the sum of how many terms? 7. Look in your notes and you'll see. The other problem we knew we were finding the sum of how many terms? 11. Look in your notes and you'll see that. So this formula here, we've already learned it today. This formula is when you're trying to find the sum of a geometric sequence, okay, when you know the number of terms you're adding. The number of terms you are adding, okay? But when you don't know the number of terms you're adding, like these problems back here, like I taught you, an infinite geometric series, then you use this formula here. Do you see the difference? You use this one here when you're finding the sum of a geometric infinite series, an infinite geometric series. So this formula is for the sum of an infinite geometric series. In other words, you don't know how many terms you're adding. You don't know. And that's when you use this formula. So you need to understand that and make note of that and not confuse these two. They're both used to find the sum of a geometric sequence. But this one is used when you know the number of terms you're adding. This one is used when you don't know the number of terms that you're adding. Okay, let's go ahead and I want you to find the sum of these terms. Okay, copy this down. Now, first of all, in this problem, do I tell you how many sums we're going to add? Or excuse me, how many terms we're going to add? No, I don't. So it's an infinite geometric series. Okay, fair enough. Which formula do you use? Well, we use this formula right here. Now, let's find the common ratio. The common ratio for this is 3. We're multiplying 3 over and over and over. Hold it. Ding, 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 ding. A red light should go off. Let's go back and look at our notes. You can only find the sum of an infinite geometric series when R is in this sweet spot right here between -1 and 1. Remember, we'll look at your R. Your R is 3. And 3 falls way over here outside your shaded region right here. So when that happens, you simply say no solution. Do you know why you say no solution? Because you cannot find the sum of this infinite geometric series. It's impossible. It cannot be done. Notice the numbers are getting bigger and bigger and bigger, and we would have no idea how many terms we're adding. Thus, we do not know what the sum would be of this infinite series. So let's continue to the next problem. Let me get a drink of water here. Please copy the next problem down. All right, now let's see if we can find the sum of this series. Now, did I tell you how many terms we're going to add? No. So we know we're going to use this formula here. Next, let's see what our common ratio is. Well, our common ratio is -1/2. If I take this term here and divide it by this term, I get -1/2. If you then take -1/2 and multiply it by each term, you'll see you get the next number out. So does my common ratio fall in my shaded area, -1/2? Well, let's see. Here's my little domain right here I have to have right here, and -1/2 falls right here. So yes, I can definitely find the sum of this infinite geometric series, and here's the formula I use. So the sum of, are you ready? I put infinity is what I put. Now, if you don't put that, I'm not going to get upset at you. I just put, we don't know how many terms, so I put the sum of infinity of all the terms is a subscript 1, that's my first term, -2 over 1 minus r. 1 minus parentheses -1/2. Now, you would expect this to be a lot harder, but it's actually easier. So I would have -2 over 1 minus a -1/2 is 1 plus 1/2. That would be 3 over 2. And then if you take -2 and you divide it by, let me look at my notes here real quick. If you take -2 and divide it by 3/2, you will get out -4/3. So you know what we call this answer? We say this answer is the what? Sum. Or we can also say this answer is the limit. And what that means is this. Now, are you listening to me, guys? I don't care if you keep going in this series, 200 terms. I mean, you keep going and going and going. If you add them all up, they'll keep getting closer and closer and closer to -4/3, but it will never quite hit -4/3. So even though the sum is not quite 4/3, mathematicians call this the sum of the infinite geometric series, or we call it the limit of the infinite geometric series. Okay, so I hope that makes sense. You use this formula here when you know how many terms you're adding up in a geometric series. You use this formula when you don't know how many terms you're adding up. In this one here, you cannot use this formula unless r is less than 1 and greater than -1. Okay? If you got to replay it. Make sure you know this, all right? Now, I want to do 2 quick word problems, 1, 2, and then we're done for the day, okay? Please turn your books to page 869, example number 8. I'm turning over there right now myself, page 869, example number 8, and I'm going to read the problem to you. Suppose someone offered you a job, and they said, I'm going to pay you a penny the first day, and then I'm going to pay a penny, 2 pennies the second day, and then 4 cents, and then 8 cents, and then 16 cents. In other words, if you look at the problem here, it says they're doubling your previous day's salary. How much would you earn? Now, you could do this the long way. I mean, you could list out 30 terms, and by the way, there's 30 days in September, so that's why we're using 30. You could list out all 30 terms. That would take you quite a while, and then you could add up all 30 terms. But there's really no need to do that. If the first day you make 0.01, and the second day you make 2 cents, and the third day you make 4 cents, and the fourth day you make 8 cents, and the fifth day you make 16 cents. We have a geometric series here, guys. We're going to add all of these up to see how much money you made in 30 days. Mr. Earhart, are you sure we have a geometric series? Let's find out. If you take 0.04 and divide it by 0.02, guess what you'll get out? 2. So now take the number 2 and multiply each one of these by 2, and you'll see you get out the next number. So I know that my first term is this. I know that my common ratio is this. Now, here's the problem. Are you ready? Are we going to use this formula here? Or are we going to use this formula here? Well, I have a question for you. Do we know how many terms we're adding up, or do we not know? Yes, we know. We know we're adding up how many terms? 30, right? So that means we're going to use this formula right here. All right, so I'm going to see if some miraculous way I can actually do something right here for once with my program. All right, there we go. And I don't think I did. I put it on the wrong page, didn't I? There we go. All right, so there's our formula. So let's see if we can't find this sum very quickly. The sum of 30 terms equals a subscript 1, that's 0.01. 1 minus, now my common difference would be, or my common ratio is 2, to the n power, that's 30, all over 1 minus r, so 1 minus 30, and that blob right there is 30. Now I'm going to type, first of all, let me tell you, for the top of my fraction here, I'm going to go ahead and type in 1 minus 2 to the 30th power. Be sure and put the 2 in parentheses. So it's 1, then minus, then put your parentheses, then 2, then close your parentheses to the 30 power. If you do that, you're going to get a huge number. It looks like it's 1,073,741,823. Okay, and so I'm going to have to kind of make a little room here. So negative 1,073,741,823. And again, I think that's 1,073,741,823, all over negative 29. Now, hopefully you didn't clear that number off your screen. Hopefully that's still on your screen right there, because now you're going to hit times 0.01. So times 0.01, and you're going to get, I'm not going to write it down, but you're going to get negative 1,073,741,823. And then divide that by negative 29. And you're going to see that you're going to come away with a very nice salary. And actually, guys, hold on one second. I apologize. Mr. Earhart hates it when he makes mistakes, but I shouldn't put a 30 here, should I? And I'm sorry, guys. It's 1 minus r, and your common difference was 2. So I'm sorry. So 1 minus 2, this should be a negative 1 right here, and I apologize. So if you take that top and, hold on one second, and you divide it by negative 1, you're going to get a very nice salary of $10,737,418. Isn't that interesting? If someone would have told me they'd pay me a penny a day, but they would double it every day for 1 month, I would have thought that I would have made maybe a couple $100, you know, $300-400, but that's just not how it is. Once that thing starts doubling, man, I mean, think about it. When you get to 100 and it doubles and it's 200, then 400. So anyways, it's a lot bigger than what you thought. So there's the sum of your first 30 terms. All right. Okay, one more problem. And again, I apologize for this mistake. I hate that when that happens, but we all make mistakes. Okay, page 870, number 10. Page 870, number 10. Okay, students, I'm going to paraphrase the problem. Large sporting events have a significant impact on the economy. Did you guys know Chattanooga used to host the NCAA Division II or Subdivision Football National Championship at Max Finley Stadium? We did that for years, and that really helped our economy. Now, I think it's been the past 2 or 3 years, they no longer have it here. They have it in Texas, and hopefully one day we'll get that back here. And it was really good for our economy. And so, whenever large sporting events have come to a certain city, they have a significant impact on the economy. Those attending the 2006 NCAA Men's Final Four in Indianapolis, and by the way, one of my friends went there. His name is Wayne. He went up and he went to that Final Four. When this happened, they poured $45 million into the local economy. Now, assume that 60% of that money is spent again, and then 60% of that money is spent again, and so on. This is known as the economic multiplier effect. Find the total effect on the economy. Now relax. Just think this through and watch. Okay, let me get a drink of water here. All right. Every year, we're assuming that 60% of that money is put back into the economy. So, with that in mind, we know the first year, in 2006, 45 million. Now, next, if you take 60% of that, I'm getting my calculator out right now, guys. It says out of that money, 60% is spent again. So if you take 60% of that, you're going to get 27 million. So the next year, 27 million was spent, poured back into the economy. Now multiply that by 60%, and you're going to see that the next year it was, and I'm looking here, 16,200,000. And then we multiply that by 60%, and we're going to see the next year 9,720,000 was put back into the economy. In other words, investors, people buying things, spending money. So it really has a trickle effect. When a big sporting event comes to your city, it doesn't just affect you that one year, it continues to affect you at a decreasing manner. And if you'll look, each one of these are being multiplied by 0.6, 0.6, 0.6. Do you see that? If you don't believe me, try it. You can take this number here, divide it by this number here, and you'll get 0.6. And then if you take that 0.6 and multiply it over and over, you'll see you're getting out the next number. So I have a geometric series. And I'm going to add all of these numbers because here's why. If you look at the problem, look what it says. It says, find the total effect on the economy. Now here's the problem. Are you listening to me? Does it tell you how many years they want you to figure this? No, we don't know where to stop. So if we don't know where to stop, then do we know how many terms that we're going to add up? No, it doesn't tell us if they did not tell us if they want us to find the effect that this sporting event had on the economy for 5 years or 6 years. It didn't tell us how many years. So we don't know how many terms. Hold on 1 second, please. And that's not what I meant to do. Hold on. So we're going to have to use the formula right here. This formula here, guys, is the one that we use when we're finding the sum of a geometric series and we don't know how many terms that we're dealing with. Okay? It's right here. This is the one. So that's the formula we're going to use because we don't know how many terms we're going to be adding. Now, you cannot use this formula unless r is less than 1 and greater than -1. I'm at 0.6. Think of your number line. Here's 0, here's 1, here's -1. Where does 0.6 fall? It falls right here. So we're good. As long as the r falls in here, we know we're good. So we can use this formula. So here we go. The sum of an infinite amount of terms equals my first term, which is 45 million, divided by 1 minus r, which is 0.6. So I really have 45 million divided by 0.4. 45 million, let me type that in, divided by 0.4. And if you do that correctly, you're going to see that the sum, or what else do we call it? The limit of this infinite geometric series is, and it's right there in your book for you can look at it. It's also on your calculator if you typed it in correctly. 112,500,000. And that's a lot of money. And so that shows you the impact of one big sporting event that comes to your city. It continues to impact your economy for years and years and years to come, up to how much? This much right here. And of course, this sum right here is all influenced by how much money was made that first year. Okay, but there you found the sum of all of those terms. Hope that made sense, guys. If not, you might want to watch it again, but there's no homework. I told you that, no homework, so enjoy that. Let me go ahead and give you the homework that we're going to be working on tomorrow. And if you want to get a head start on it, you can. If you don't, that's totally fine. It's going to be page, and I have it written down here. Let me look. It's going to be page 872, numbers 1 through, and it looks like, I'm not sure why I did not include the word problems. I really would like to. Let's go 1 through 43. And I did have this written down, but now I'm starting to second guess myself. Every other odd, so it'd be like 1, then add 5, do add 4, then add 5, add 4, and do 9, etc. And then I want you to pick up and start with the word problems 51 and do those 51, 55, 59. We'll just do 3 of those. So 51 through 59, every other odd. So really it's 51, 55, 59. So three word problems, okay? So this is what you're going to work on tomorrow. You do not have to do it today, but if you want to get a head start, you can. If not, that'll be tomorrow's assignment. Hope you guys have a good day. Call or email if you have any questions.